All right, we're ready to start the next section for our Project 2 demonstration for RTDSP. So previously we talked about coding in C, and we coded those moving average filters. And there were two main problems with the basic implementation of those moving average filters. The first problem was if there was a large number of coefficients, it would take a long time to type out all those numbers. And the second was the inefficiency due to using the shift register. Well, in this part, we're in the next section, section 3.4.2, we're going to address the problem of writing out all those coefficients. So instead of writing out all those coefficients, we can generate those coefficients and put them in a header file. So with this, let me close all these out and open up the correct project. So for this project right here, instead of typing out all those coefficients, we instead included a new header file, this coefficients.h. This will load those coefficients from a separate file into the program, so that way you don't have to type them all out. So instead, you have to create a file with all those coefficients inside them. How to create this file is there is a script in the book that allows you to convert matrices or vectors in MATLAB into C files for coefficients. So I took the original file to convert coefficients into a C file, and I modified it to include an FIR filter to generate some FIR filter coefficients. And I'll get into implementing this a little later. But for now, we're going to generate those coefficients from this header file. So if I open up this header file, it contains the order and an external float, and it's in the separate C file, and this is where the coefficients are located. So this is the coefficient file given as an example in the book, and it has a total of 31 coefficients with an order of 30, and according to the confidence lines, it's a 5 kilohertz low pass filter at 48 kilohertz sampling frequency. So to check the sampling frequency, we can go to the DSP configure header, make sure that we have 48,000 selected. And so with these coefficient files, I can go ahead and just run my DSP or download my DSP code onto the board. So nothing else down here has changed. This is still the same. You still take the input, put it in the first slot of the buffer. You still do the dot product. You still shift using the shift register and write the output. That hasn't changed. The only thing that's changed is now we've incorporated all of our coefficients into this file. So if I run this, once this is done downloading, we can run this. So it's a low pass filter, anything below 5 kilohertz. I don't want to put anything higher than 5 kilohertz in there because that would be high pitched and might cause headaches. So you're just going to have to take my word that I'm going to have to trust the book's word that it's going to be a low pass filter with 5 kilohertz. That's its cutoff frequency. If I see the 1 kilohertz sample passes through, no problem. 2 kilohertz sample, and you can see they're getting higher pitched. I don't want to go, okay, 3 kilohertz is getting through, and I think that's about as high as I want to take it for now. So, but the main idea is that you can put those coefficients into a file and then output them, and be read by the program, and then be used to create your filter. So with that in mind, going back to what I was talking earlier, this coefficient file was generated or was given to us in the book's code, but we can generate our own coefficients using this MATLAB code. And I incorporated my own FIR filter generation FIR filter code into this program to generate the coefficients for an FIR filter. So the main thing about the FIR filter is the number of taps. And so I talked about this earlier, that if the sampling frequency is higher, that means there's less time in between samples, which means there's less time for calculations. So there's less time for calculations. If we look here in this loop, that means there's less time to form this dot product loop, so you can't have as many taps. So the number of taps that your FIR filter can have is limited based on the sampling frequency. After running some experiments after running some experience right here, I've determined the maximum number of taps for the shift register that can be used for each sampling frequency is listed here. So yeah, 8,000, you can have a maximum of 723 taps. Now this isn't in an actual implementation, you don't want to use exactly 723 taps, because this is only if the only thing it's doing is performing this dot product. If this code needs to perform other things such as like other additions or multiplications, then you don't want to use exactly 723 taps, because then you won't have enough time, because this uses all the available time based on my test. So if there's any additional operations you need to perform, you can't perform them unless you lower the number of taps even more. So with that in mind, we're going to test this out. I'm going to use 8,000. So I'm going to use the 8,000 taps, maximum 8,000 taps for the shift register. And I'm going to create an FIR filter with a cutoff frequency of 1500 hertz. So if I run this code, this is what my filter will look like. It will be a low pass filter, and at 1500, it will cut off. So the main thing about this code, after I ran, I'm going to talk about it a bit. So this whole top part up here is just generating those FIR filter coefficients. So I shape my frequency response, and then I use the IFFT to shift it. Let me roll a little bit more. So the frequency response, I shape my frequency response. Then I shift my frequency response from the frequency domain to the time domain using IFFT. And then I extract the coefficients from the time response. And so these become my coefficients. From these coefficients, I'm going to store them in this location. This is just the file path to my project. And the variable name is going to be B, because that's what the original was before. So the coefficients are going to be those extracted coefficients from my FIR filter, the FIR filter length, and then this code is all provided by the book to write into the C file. So since I ran that code, I should have those coefficients into a separate project for my shift register, which is going to be this MATLAB shift register. So I'm going to close out of these, because we're done with that example. It's just an example using 31 taps, but we're going to now look at this MATLAB shift register. So this is the same as the example code, exactly the same. So exactly the same. Even this code is the same. The only thing different is what's inside this coefficient file has changed. So if I open up coefficient H, notice how the file size is now 723. And so we have all these samples. We have all 723 samples. All 723 samples from that we got from here, because that was the maximum number I could get based on my experiments. So these are all my coefficients. So then I need to check my settings to make sure that I'm not at 48 kilohertz, that I'm at 8 kilohertz, just to make sure that, oh yeah. So just to make sure that I'm at the right sampling frequency as in my code, so that way it'll work out. So with this in mind, I can run the code now. So I run this code. It's finished downloading. All right. All right, so now we can test it. So let's take the 1 kilohertz signal, pass it through. You can hear it just fine because it goes to the low pass filter. And then we try the 2 kilohertz. Nothing. You don't hear any sound no matter how much I turn up the frequency, because it's been attenuated because of the number of taps. So that brings us to an interesting question: is what happens if there are too many taps? The processor can't perform all the calculations in time. So what happens there? So if I go back to my code using the same 8 kilohertz, but let's say I increase the number of taps by 1. So now there should be too many taps. The filter or the DSP board cannot perform enough calculations in time. So with this, now I go back into here, but if I look at my coefficients now, let me just do that real quick. So if I go back in there, I should go into this one. 724 instead of 723 now. That's the main difference. We just added one more tap, left all the other settings the same. So if I run this, notice how as soon as I just add one more tap, immediately the DSP processor is causing there's some problems with the DSP processor because it's spitting out a tone, and a very loud one at that. It kind of surprised me, but I'm not even inputting any sound signals right now. This is just by itself. So even if I input the sine wave, you can barely, it doesn't really change anything because the number of taps is too high, and so it can't calculate an output in time. So that's what happens when the taps when there's too many taps. So you never want to put too many taps for the DSP filter, otherwise you'll just get garbage at the output. So let me just pause that real quick so I don't have to hear that. So that's the number of taps. So like I said, I did this experiment for all the different number of sampling frequencies. So if you notice that as the sampling frequency goes up, the number of taps goes way down. So like when you're at 48,000 or 96,000, the number of taps has gone down to 100 or 50. And it appears somewhat linearly. So notice how if I double the frequency, so if I double from 8,000 to 16,000, the number of taps approximately gets cut in half. So, and then again, if I double the number of taps, if I take 16,000 double to 32, 175, that's slightly less than half, but so it's not exactly a linear relationship, but it can be almost approximated as a linear relationship. So we can try this again, but with a different number of taps. So let's try, we can do 48. So I also have to change the sampling frequency. So this is 1, 2, 3, 4, 5, 6. So we're going to 6. We're going to still use cutoff frequency of 1500. The max taps at 48,000 shift register. I run this. So this is going to be 114 taps. So if we go back in here, I look in here, 114 taps. Make sure you change the sampling frequency back to 48,000. I run this. Yep. Yeah, that's the error noise from before when I put too many taps in. Oh, that's kind of loud. I'll just take that out. All right. So 1500 is our cutoff frequency. So if I put in the 1000 kilohertz signal, you get an output. And if you put in a higher frequency, okay, I just grabbed 3000, you get nothing because the filter will filter it out. But let's see if I grab 2000. So if I grab 2000, notice that if I turn up the volume to max, you can hear a slight 2 kilohertz sound, even though my cutoff frequency goes 1500. And that's a problem with the filter itself. So the problem with the filter is that if you have less taps, the filter becomes less accurate. Notice how there's these oscillations. Usually these oscillations are caused by, I believe it's Gibbs phenomena. But if I look at where 2 kilohertz is, it's not actually attenuated to 0 because it's part of these ripples down here. So it's attenuated greatly, but it's not exactly 0. So you can still hear it. So we want to grab as many taps as possible for an accurate filter. So the 8000 filter, if you remember, the 8000 tap filter was very smooth. It didn't have any signals at 2 kilohertz, but it required a lower sampling frequency. But if we increase the sampling frequency, we decrease the number of taps, and now our filter is not as effective. And if you want to know if we take just one more tap, I just add one more tap here. That now, just like before, so the number of taps is increased by 1 to 115 now. If I run this, you won't get an error per se, but the DSP board will spit out and pretty much garbage. It'll spit out a tone immediately, even if I don't input a sound signal, because it takes too long to calculate. So yep, there's that error tone. Don't want to hear that for too long. So that's the shift register, or that's using the coefficient files to generate those coefficients quickly for us, because notice how by using this MATLAB code, I didn't have to type out all 115 or 700 coefficients for each of these filters. So that's a way to quickly generate the coefficients I need for my filter. Now, the next part we're going to address the problem with the shift register. So the shift register is is not as efficient because you have to perform an operation to shift each individual value over. And as we talked about, or as we demonstrate here, each operation takes up precious time. And we need that time, and that time controls how many taps we can put in our FIR filter. So if we can make our shifting process more efficient, then I can increase the number of taps here and get slightly more accurate filters. So in the next part, or in the next video, we're going to talk about using a circular buffer, which is more efficient than the shift register, which can help us increase the number of taps in our filters slightly.